when you're talking about matter, you need to know about what is meant by kinetic model of matter. Now, matter, whether it's solid, liquid, or gas, they are often composed of small particles that are always in constant motion. These particles are what you know as atoms or molecules. And depending on how these atoms or molecules are arranged, it will determine what type of state it is, whether it's solid, liquid, or gas. For solids, the molecules are often packed very closely together and held in place by strong intermolecular bonds. These bonds prevent your molecules from moving, giving them their solid rigid shape. And the molecules are often arranged in a regular pattern and vibrate about fixed positions. So this last statement here is very important because sometimes you may be asked about certain characteristics about molecules that are arranged inside and solid. And then when you move on to liquid, the molecules are still close together, but they are no longer in a regular pattern, unlike solid. So the molecules have enough energy to break the intermolecular bonds between them. They are able to slide past each other, thus allowing liquid to flow. Okay, so again, this last statement here is also quite important when it comes to liquids, right? They are not in a regular pattern. They are able to slide past each other, giving them their flowy characteristic. Then when you're talking about gas, molecules are widely spaced, usually 10 times further apart than what you find in liquids, and they tend to move about freely and randomly at high speeds, and they tend to have no intermolecular bonds between them. So the large spaces between the molecules often mean that gases can be easily compressed or expanded. Okay, so these are some basic characteristics of solid, liquid, and gas that you may be tested inside your exam sometimes. Okay, it doesn't come out that often, but it will come out, just that it's not as frequent. I think the most recent one was the last exam sitting about 2-3 exam sittings ago, where they ask you about how is the molecular arrangement inside a solid. Okay, now then after that you move to the next page, you need to go through something called internal energy. Now, when you're talking about matter, as mentioned before, you had three different states of matter: solid, liquid, and gas. No matter which state you are considering, the molecules are either moving or vibrating about. So because they're moving or vibrating, they tend to have kinetic energy because of their motion. So right now, if you consider that you have, say, gas here, and you have a number of molecules inside this volume of gas here, these molecules tend to move about in random directions like this or like this. Okay, so they have motion, they have kinetic energy. Now you imagine if temperature increases, the temperature of the gas is increased, these molecules tend to move faster, so the KE increases. Here you can actually make a conclusion saying that molecular kinetic energy is actually directly proportional to your temperature in Kelvin. This one will be something that you have either learned in chemistry before this or in your ideal gas chapter if you've already learned it in school, where they tell you that mean kinetic energy of a gas molecule is 3/2 kT, such that mean kinetic energy is proportional to temperature. Okay, so your molecules, regardless of whether they're solid, liquids, or gases, they tend to move about. They have kinetic energy. If you increase your temperature, they're going to move faster. You're going to increase their KE. Okay, now for those molecules that you have inside your object, doesn't matter again whether it's solid or liquid or gas, they tend to move about with different speeds. They won't be moving with the same speed. They will all be moving with varying speed. So say maybe this one was moving at 30 meters per second, this one was moving at 20 meters per second, this one is 10 meters per second, this one is 5 meters per second, this one 8 meters per second, and so on. Okay, this is just an exaggerated case. So those molecules tend to move with different speeds. They tend to have random values of kinetic energy or varying values of kinetic energies. Okay, so this is talking about the molecular KE. Now you move on to molecular potential energy. When you're talking about the molecules in any states of matter, they also tend to have molecular forces, intermolecular forces between them. due to the attraction of your negatively charged portion of one molecule with the positively charged portion of another molecule. Say, for example, when you talk about a hydrogen chloride molecule, let's just say you have HCl and another HCl here and another HCl here. This is your hydrogen chloride molecule. The hydrogen part of your molecule here tends to be positively charged, whereas the chlorine part of your hydrogen chloride molecule here tends to be negatively charged. So if these molecules are close to each other, what could actually happen is that you would have intermolecular forces of attraction between them. You see, this chloride portion will be attracted to this hydrogen portion, whereas this hydrogen portion will be attracted to this chloride portion. So there are intermolecular forces between them if they are close enough. So this is what we call as your intermolecular force. Okay, so if you want to increase the separation between these molecules, you actually have to overcome these attractive forces. You need to do work to overcome them. So this work that you do actually goes into increasing some form of energy. The energy that you're increasing here is the potential energy, okay? So you want to increase the separation between the molecules here, you need to overcome the attractive force, you have to do work, and this goes into increasing your potential energy, molecular potential energy specifically. So if your separation increases, your molecular potential energy would increase because you're doing more work now to increase the separation, okay? And then when you're talking about bonds being broken between the molecules, molecular potential energy also increases, okay? Now, when it comes to the value of the potential energy between the molecules, just like for kinetic energy, the values are always different, okay? Because as you think about, if you think about it, molecules in a body tend to be at different distances from each other. This is especially true for liquids or gases. So they'll be varying or random potential energies, okay? Now, for molecules, just now we went through the part where we said that it has molecular kinetic energy and also molecular potential energy. If you were to sum up all these molecular and potential energies, it will give you something called internal energy, okay? If you sum up the random values of all these molecular potential and kinetic energies, you have a particular quantity called internal energy. Now, internal energy is formally defined as the sum of a random distribution of kinetic and potential energies of molecules in a system. Okay, so you need to have the word random here in your definition because here, just now as I mentioned, your molecular Ke and your molecular Pe all tend to have different values. Okay, so when you sum it up, you're actually summing up all those random values, all those different values together. Okay, that gives you your internal energy. So if you write it in equation form, you can just say this: IE is equals to Ke plus with Pe. Okay. Now, because internal energy is equals to Ke plus Pe, this also would mean that change in internal energy is the sum of the changes in your kinetic energy and potential energies of molecules in the system. So meaning to say IE equals to Ke plus Pe will change to change in IE equals to change in Ke plus change in Pe. Okay, so this is one thing to note. Now, for the case of ideal gases, you need to be careful a bit. When you're talking about ideal gases, an ideal gas has no intermolecular forces. So there are no molecular potential energies. Because if you recall what I just mentioned about molecular potential energy, it comes about because of the attraction between your molecules. So by definition, an ideal gas has no intermolecular force. So it will not have any molecular potential energy. So if you do not have potential energies, your internal energy equation for an ideal gas would just be IE equals to Ke. Because if you say that ideal gas has no potential energy, this part is zero. You're only going to be left with IE equals to Ke. Okay. And subsequently, if IE is equals to Ke only, you could also say that change in IE is equals to change in Ke. Okay. Now, there's also another different relation that you'll be able to derive from there. That one being that because Ke of molecules is directly proportional to thermodynamic temperature, You could also say the internal energy of an ideal gas is proportional to your thermodynamic temperature. Because just now I told you that mean kinetic energy is equals to 3 over 2 kT. That means mean kinetic energy is proportional to T. Okay. And now you have internal energy equals to KE. If you put this one inside, you will get IE is proportional to T. Okay. That's what this statement here is supposed to mean. Okay. Now, then after that, you move on to the next part where you talk about phase changes of matter during heating. Now, sometimes you may be asked to explain what happens to the internal energy of an object that is being heated. What actually contributed to the internal energy change? So say for example, right now you're trying to heat a particular material or substance from solid form to liquid all the way to gas. Okay, say maybe you're trying to melt ice. Okay, so if you look at section 1, maybe you're trying to melt ice now. Let's just take the example of you trying to melt ice. When you supply heat, let's just say right now from here to here, you are continuously supplying heat. So let me just write it out. This is heat being supplied. So you're trying to melt ice right now. You supply heat to it. When you try to heat it up, you expect to see something like this. It could be that maybe this one is ice at negative 10 degrees centigrade. You heat it out to 0 degrees centigrade. Okay. So here, when you supply heat, the heat causes the temperature of your solid to increase until the melting point at 0 degrees. At this stage here, in section 1, your internal energy is increasing because your molecular kinetic energy is increasing due to temperature increase. Just now I mentioned to you that your molecular Ke is proportional to temperature. When temperature increases, Ke increases. Because you can see that there's a temperature increase here, you could say that your molecular Ke is increasing. And then how about your molecular potential energy? You could also say that your molecular potential energy is increasing because there's an increase in your molecular separation. Okay, so this one, molecular PE also increases. In your case, your IE increase because your KE increase and your PE increase. Okay, now how about the part where you heat your solid up to the melting point? You heat it up, you heat up the ice up to 0 degrees centigrade. So here is where you start to have some sort of phase change where your ice changes to water, it melts to water. This is section number 2. Now, during this point here, any continued heating will not cause any further increases in temperature because your ice is trying to change to water. So it won't continue increasing until all your solid is melted, until all the ice has melted. Now, specifically at this stage here, what can you say about your molecular Ke as well as your molecular Pe? In your case here, because your temperature did not change, you are still at the melting point, your molecular Ke actually does not increase. There's no change in your molecular Ke. Okay? All right? But what you can say is that there should be a change in your molecular Pe. Okay? Now, you consider this, your heat supply causes a phase change from solid to liquid. Okay? When you go and change it from solid to liquid, you are actually increasing the separation of your molecules slightly. So this one increases your molecular PE. But at the same time, when you go and change your substance from solid to liquid, when you melt ice into water, what actually happens is that your bonds are also being broken. Okay, bonds are actually being broken here. This one also contributes to your PE increase. So if I just write out your IE equation here, internal energy is equals to kinetic energy plus potential energy. Because there's no temperature increase, you do not have any KE increase. Okay. Because you do not have any temperature increase, this one, your case here is that KE has no change, okay? But your PE is increasing because of two things. You have separation increase and also bonds broken, okay? So your IE here is considered to be increasing. Actually, in general, as long as you supply heat when melting your substance, your internal energy will actually continuously increase, okay? So this one I better just write it here first. So long as you supply heat to your substance as you're heating it, your internal energy will actually continuously increase. Okay, there's no part in your sections here where the IE doesn't change or the IE suddenly drops. It will just keep on increasing. It's just a matter of whether the IE increase is contributed by the KE or PE. Okay, so when you go and melt your ice into water and you've completely melted that ice into water, you will now go on to section 3 now. Okay, this part here is where you're trying to heat your liquid all the way to boiling point at 100 degrees centigrade. So in your case here, internal energy is still increasing. Okay, in your case here, in section 3, your temperature increase, your molecular Ke will increase, your separation increase, so your potential energy will also increase. Okay, so this section 3 here is actually a repetition of section 1. And then when you reach boiling point here, this section 4 here is a repetition of section 2. Okay, so the explanation as to why the internal energy increases will actually be the same as the first two sections that you see here. Okay, so this is just one thing to note.